Awesome. Well, I'm really, really excited to be here today. So how many folks here in the audience, I mean, if you're here doing for Python, how many of you do Python today? Okay. How many do SCIKIT today? I'm just trying to get like, okay. How many tried H2O's Python API like this summer? Okay. Good. Okay. That helps. So yeah, like Brandon said, I'm a customer-facing data scientist at H2O, which means I'm out working with everybody that uses our product that I can to get like community feedback and see what we should do. And so one of the things we heard this summer was the first version, second version of the Python API needed some improvement. So we went out and we listened very strongly to the Python community. It was really a new community for us to get involved with. Very strong, obviously, in the Java and R community, but a newer community for us. So what we heard was very clear, like we want a Pythonic interface, something that reminds us of hacking in Python all the time. But it also has to do everything you get from the R interface. And then I think like the next two are kind of the soft things that data scientists want, but they're really important, right? We need an interface that lets us rapidly learn and iterate. So we want to stay inside of the tools that we're used to using and just go really, really fast. We heard from businesses like we've got this existing skill set. So this is a little different than sometimes coming from R. You know, the Python community has a couple strong players in the community. There's a lot in the PyData community, but there's a couple strong players. You know, there's SCIKIT and there's Pandas. They said, look, we really want to leverage these skills, and you should cleanly interface with them. And oh, by the way, like we'd like to go to Spark too because we love Scala, but you know, Python and Spark's also very important to us. And then, you know, one of the things that's maybe a little different from the R community is the Python community. A lot of times the Python community they could take things all the way into like production apps. So they said, like, give us a clean path to getting to production apps with some things. And you've already heard about some of those today at the conference. So some of those are a repeat, and I won't go into too much detail on those, but we heard that very cleanly. So being a data scientist, I don't like to work on things without having a motivating example. And I have a background in dealing with things that when you drop them on your toe, it hurts. So it turns out not to be jet engines, but there's this great kind of data set out there that NASA produced as part of a 2008 challenge, and it was all about picking up 23 sensors from these 40,000 pound thrust jet engines as simulated data, because you can't actually destroy that many jet engines. You can, but it's very costly. But running them to the end of their remaining useful life, and there were a few challenges with this. One of them is that there were two different failure modes the engines went into. They all came out with different manufacturing variabilities. All that was synthesized. The sensors all had different bias and noise in them. And then the engines were operated in 6 different operating modes. And you didn't actually have too big of a training data set, 250 jet engines run through the remaining useful life. But I love data sets like this. They're time series data sets. They're the Internet of Industrial Things data sets, and they're challenging data sets. So it kind of let us, it was one of the many ones. You can find many more on the H2O GitHub, all in open source of like examples of using the Python API. This is one I'm going to show today because I need like a motivating example. For me personally. And the other reason that I like this, I get to say the word brontobytes. This is a chart from HP, and basically the claim is like the Internet of Things is going to bring us a lot more data than we're used to dealing with today. So you can see actually terabytes way down here in 10 to the 12. So you know the data that's going to come off of sensors and connected things is going to be gigantic, and you know, so we need to start and figure out how our tools are going to deal with that. So this is my motivating example. So I'm going to throw in. So I got 2 goals for today. One of them is throw in this data science example because I like motivating examples, and then 2, talk about the Python API so you can see what all's in there. So the first thing, I mean, I'm going to do some call-outs through this. First thing is loading data in Python looks like loading data in R, H2O, or if you're using Pandas, you just simply upload a file or import a file just like you do today. In this case, this data came with no column names, so we changed the column names after import to the right set of column names. Oh, before I go on, there is an IPython, I said this once at ML11, I got in trouble. There's a Jupyter notebook that is available. So we'll publish this Jupyter notebook that actually has this whole example available to you afterwards. You know, it seems like little things, but like we now, you know, are PIP 8 compliant with our names. Our names are lowercase with underscores in between them, so that becomes important for the Python community. You can ask for summary statistics on the data frames once you load them. You get all these kind of summary statistics by date or by column. You get the types, what the mins, and all that sort of things are. And you get the first few rows. Actually gives you the head of the data, which is a plus over some other tools. I mean, it's a little thing, but it lets you get in the flow very, very quickly. So that's kind of like all basic and straightforward for getting started. So the next piece is like, we wanted you, so all this is an H2O frame, right? This is all inside of H2O. So this all operates on data at scale parallel across the cluster of computers, which I really think is one of the things that H2O brings to the Python community that really isn't in the PyData stack today, which is a parallel and distributed data frame and machine learning framework, right? So that's a little different than like, you know, there's all these different tools inside of the PyData community, but this is the place H2O kind of occupies and can bring to that community. So that's the reason I'm showing this is, you know, feature engineering is done with these. This is a very basic sort of feature engineering step. Go group by some category, calculate some summary statistic, and reapply that summary statistic back to the original frame that I'll use for learning. So that's what this is actually doing. The data didn't actually it told you which cycle number is in, so you have jet engines and they're being operated through cycles. You actually just need to reverse that and figure out like how many cycles it is until the machine's dead at the end of its remaining useful life. So this is kind of the steps for doing it. Doing a group by, calculating the summary statistic, that's what the max does here. Give me back that frame. Merge that back into the original data frame that was available. So this is a function that does this. And then calculate the remaining useful life and add it. So I think this should be fairly familiar with people that are used to kind of using maybe pandas for doing this execution. So you can do all of this sort of data prep work before you get there. And all the things you've seen before about strings are also available. Boolean indexing, so if you need to get a number of rows out of the data, you know, in this case, I'm actually pulling out a sample of the data, but Boolean indexing works for selecting the number of rows. It also works for selecting which columns if you want to pull out a subset of the column. So I'm pulling out 3 jet engines is what this basically does, and gives me a Boolean index that I can then pull out of the H2O memory space into the Python memory space. And that's nice, right? Because then I can use all these tools that I'm used to using in the Python space for doing some exploratory analysis. So in this case, my tool of choice is Seaborn. If you're not familiar with it, it's a cool charting tool for statistical data. And that's really what I'm showing here is that you can just pull it out and we'll sit right there inside of the notebook and just kind of keep going. This one's actually an interesting piece of data because what I have is, this is data over time. So this little 0 remaining useful life happens right here. And I can't tell any difference between what that data looks like and the data at the beginning of life of one of these machines. So I actually can't make any predictions yet on when these machines will fail. So this is what made it a really great motivating example, is that it's actually kind of hard. So one of the things you can do, again, is taking that exact same training frame, just do some plotting. We actually found out the sensor data happens in clusters. Like all the sensor data is clustered together. It turns out it's in 6 clusters. If you remember a few slides ago, there's 6 operating sets. So it kind of makes sense that the sensors move around. So so this is the first time you'll actually see a piece of the new Python API for building estimators, and you're going to see it a couple more times. But the way it works is that you import your estimator, whatever type of estimator you want, a k-means estimator, generalized linear model estimator, a gradient boosting machine estimator. You set up the parameters of the estimator, which is what this k-means estimator is. It says set k, the number of centers, to the operating mode. And I happen to have known it's 6 because I did EDA and the data I got said it was 6. And then train on that data. So actually take the training data and build the k-means estimator. So if you're a SCIKIT user, this will look a little bit familiar to you. And it turns out those are SCIKIT estimators. And that will be important in a little bit to see. So Yeah, so then, again, common things. So I called this model-based data enrichment, where I went and built a machine learning model, cluster model, and then applied that data back in as a new augmentation into the data. So now I know I didn't have to go and I could have written rules. I don't like writing rules. I like doing machine learning. So I didn't write rules. I used k-means to then reapply, and it does a great job of kind of labeling the operating modes that those are in. The next piece, and this is an eye chart because I don't actually expect anybody to read it, but it kind of shows the level of complication that you can do with doing the data munging inside of an H2O frame, inside of an H2O cluster, all from the Python API. So what this is actually doing is it's saying for all non-constant sensor measures within an operating mode, go standardize each one of them in the operating mode. So this was actually one of the tricks to figuring out this data set is to actually do your standardization before you send it into the learning algorithm. And so that's what this does. There's some code duplication here that could probably get removed. But again, an example of using an H2O frame, you can do this on as big data as H2O can manage, and then standardize that data. And lo and behold, this is a good thing, by the way. There are now trends in the data. Those are the exact same sensor measures I showed before on the left-hand side and on the right-hand side. Now you see that the sensor measures diverge, and I had to actually pick enough of them out. The reason they diverge in different directions is because that issue with two different failure modes in this IoT data. So now, one of the things that we actually learned about this data, and this goes to time series. I love time series data and autocorrelated data and spatial data. So one of the things that was one of the things about this data is you can try to do a phase space embedding of it, where you actually embed time minus 1, time minus 2, and try to predict time plus 1. It actually doesn't perform any better on this data. So this is a great example of sometimes the simplest things with time series data just work. So it turns out one of the things that works on this data is to use the machine learning to learn a nonlinear transformation from the sensor space to a single variable, which is the remaining useful life space. That's probably another piece. There's all kinds of things you can do with time series data. I'm trying to make a prediction on things that are physical. And in this one, like I said, this phase space embedding it didn't improve the performance of the model. So you'll see that I don't actually do that. So back to the other goal of my talk, which is to talk a little bit about this Python API that I'm quite proud of, and the team did a great job putting together. Again, to build an estimator is just simply a matter of importing the right estimator, setting it up. This is a regression model, so I picked Gaussian for this one. One of the things, and you've seen this in some of the other pieces, but this kind of shows parities just through the whole product. So all of the R and Python API are really in lockstep. I mean, one might be a tiny little step above the other at any point in time, but they're really staying in lockstep now. So what this one has is it has all the things you saw earlier today around the early stopping tolerances. So this will build a gradient boosting estimator on the validation data set, and will stop after the MSE stops decreasing by 0.1%. And this is training the estimator, so it's a very simple training. You just stick out your independent variables, which are all the remaining interesting sensor variables, and how many times they were in each of the operating modes, and then just try to predict remaining useful life. One of the other things you'll see here, and so this is switching back to the interesting stuff about time series data and really autocorrelated data in general, is you got to be really careful about how you do your cross-fold validations. So there's actually a special fold column that I'm using to do the cross-folds. I didn't pick a random fold. And the reason I didn't pick a random fold is I'm actually taking 10% of the jet engines, and it's a 10-fold cross-validation, and are predicting the other 10, the remaining 10%. So I'm taking 90% and predicting the other 10. So it's a 10-fold, but it's by jet engine, I don't want to randomly pick a particular measurement at a point in time, because then you're learning about jet engines you've already seen. So it's kind of common in time series data. So just throwing in the data science piece of this and the fact that we can have all that support. Model evaluations there, you build your regressor, you train on it. You'll see previously that I had this set, I believe, to 50 trees. It stopped at 40 with the auto stopping. It gave me the model size. I got the validation, cross-validation data set, which I know is like at the bottom of this chart, but there is the cross-validation MSEs. And with the early stopping, it did everything you heard earlier in the day. It actually looked at the cross-validated data and decided how many trees to actually build in the final model. With that said, the other pieces are, whenever you're running H2O, no matter where you're running it in Python and R and Spark, the Flow user interface is available for you. So you can pull up that key that was the model. You can give it your own name. You can go into Flow and pull it up and actually take a look at the visual piece. But this was okay, but it took you out of kind of the Python flow, right? And people were saying like rapid iteration. So we have added various charting, and we'll add more plotting capabilities into both the Python and R APIs so that you can do these right inside of the tools that you see. So this is, I pulled up the first cross-validation model and plotted it here. And you can see kind of the training and validation set and how it finally reached the stopping point. So however you're using your notebooks or IPython or Python, like all that's available for you right inside of it. Again, also inside of Python and R, this isn't unique to the two, but inside of Python, we've set it up much like you're used to seeing inside of SCIKIT with its cross-validation is setting up the hyperparameter search options. So I set up the maximum number of trees to be 1,000. I tried different depths. I tried minimum rows per leaf node. I have a tendency to set the number of trees to 1,000 or 300 and actually tune the learning rate a little bit. Now that I've got early stopping, I don't even tune the learning rate. I tune how precise I want the model to be. And I just set the learning rate sometimes low, sometimes much lower than this. So I'm finding like this is one more hyperparameter I can kind of take out of the set of hyperparameters that I have to deal with now with this early stopping. You import the H2O grid search. Here I'm reusing the regressor I used before. So it is an object-oriented API, right? That you can take your object, this regressor, and reuse it with all of its settings it had. It was Gaussian, it had early stopping, all those rules, and reuse it in the grid search with the hyperparameters. And then train, and it'll do the grid search. And one call inside of the Python API, grid search, sort by whatever metric you care about, and I'm doing MSE on this one. And you can get your list of models out and the MSE on the validation set along with the hyperparameters. So it very quickly allows you to do some model comparison right inside of the Python API. So this is all kind of interesting up to this point. Let's say you want to do something more complicated. Right? I mentioned before that all of these estimators in PCA we call it decomposition are actually they're SCIKIT estimators. They implement that exact same interface out of SCIKIT. So you can put them into a SCIKIT pipeline, H2O stuff, put them into a SCIKIT pipeline. I've even defined like my specific cross-validation strategy I described earlier and wrote a custom cross-validation strategy that hit the SCIKIT API requirements and made that available. We've provided, you can put in custom scores for your cross-validation here. It does it not inside of the H2O model, but after the fact. And then I used randomized search CV just to kind of prove the point that you could do randomized search, that we could use those. I've also plugged this in. We found one that was doing something other than randomized. It was doing genetic algorithms for the searching, and it all works. So these tools that you're used to using, H2O will just fit right into them. If you do use things that are, if you keep everything inside of the H2O memory space, the Java memory space, data won't move back and forth. But if you decide you want to use one of the SCIKIT learners inside of this, it'll actually move data back and forth. So you've got to be kind of careful with that. It's just something you can't really resolve, but you can at least set these up as a pipeline and make those conscious decisions and get those all available for you. I underscored the word fit at the bottom. When you're doing it pure H2O, you use the word train. It's fit for the SCIKIT language. If you use fit inside of the regular H2O stuff, it'll work. It'll just give you a warning saying, like, I'd prefer if you didn't. So we have all of that in the Python API now. When I get done, I didn't include the slide in this, but I actually took the data that was done out of the GBM model. I'd used all the cross-validation models plus the big models. So that gave me 11 11 different models and put it into a Kalman filter. So PyKalman is a library inside of Python for doing post-processing. So since these are linear dynamic systems and you'd expect them to kind of smoothly have a remaining useful life over time, they don't just jump around everywhere, you can use some prior knowledge for ensembling the data together. And like Shri said this morning, Python folks, you know, they like to like put things together so that they work, right? So like I went out and I said like I want to put a Kalman filter on this because I believe it will improve my performance, and it did. So yeah, as a Python user, you can go get all these toolkits you're used to using and plug them around the H2O machine learning and data manipulation and have them available. I will tell you, I'm pretty proud of the results. This was a competition, and this was a top 5 result in the competition. So, and I've given this presentation the first time, but the first time I did it, I only had a couple days to work on it. So I was happy with H2O's outcome and the fact that you could just kind of plug all these pieces together. We've shown this a few times. If you missed yesterday's talk, that was given, or even Cliff's talk this morning. So Spencer and Cliff gave some talks on this, and they're really the architects of it, and it's a little bit harder to see on this screen. Often what we were hearing, and this will make it into the R API, but it's first available in the Python API. And it's mostly because the Python community could like go all the way through their full stacks. They could reuse pieces of it. So we did the same thing inside of Python. It allows this data manipulation that maybe you would do in maybe you do it in a SQL query or a Hive query somewhere, to actually do that inside of Python right now, allow your data scientists to work in a language that maybe they're more comfortable with. It won't do everything SQL will do, but it'll do big chunks of it. And this is an example of using string processing. And so with a little bit of organization of kind of doing some string processing steps here into a set of particular operations, those operations can then be taken and put into a POJO that you can then use into a scoring environment. So if you're using Storm or Apache Apex or Kafka or wherever you need to go do scoring, this Java object's available, and it will run the exact same code that you're used to seeing here. And maybe it'll make it a little bit easier, we hope, on the data scientists to simplify maybe some of their SQL queries that they have to deal with and be able to operate in tools that they're a little bit more comfortable with. And then finally, and this is actually, I wish, like McCall, which is our sparkling water Spark person, expert, everybody said, oh, by the way, we like it in PySpark too. So we're like, oh, okay, one more thing. The real trick is McCall pulled that off, so we have PySparkling water that allow you to access everything you've just seen in Python and Spark. And actually, it's only an addition to the API, and the addition is the ability to start up an H2O context inside of your Spark nodes and move data from H2O frames to RDDs and data frames. Otherwise, the Python API inside of Spark is exactly what I've shown today. So your developers that are doing H2O standalone in Python or are wanting to do it in Spark will have exactly the same interfaces available to them without doing any relearning of that. So hopefully that will provide some value. So again, this is where I started. Like, I had a little bit of a data science talk and a lot about H2O Python. These were kind of our goals. I would love feedback if we've achieved those today or later when you try it out. And kind of the way we resulted in this is we took a pretty serious look at the H2O Python framework and made some substantial improvements to it, resulting in changes to the H2O frame so that it'll look very familiar to you if you're used to using pandas and the estimator framework, and then being able to integrate it into the rest of your PyData ecosystem. So with that, I will end and take questions. Thank you.
All right, questions? I think I saw one back there.
Hi, I'm just curious about something I haven't heard yet, and that is how do you deal with errors? How do you do error propagation in this framework?
Yeah, so that's a really good question, and one that we're still working on. So you will, this may be a little scary for Python folks, but it won't be unusual for you to get a Python stack and a Java stack together in your if you run into user errors or errors on it. All those are logged, so if you have problems with it, like, there's community and support techniques, but yeah, it propagates an error code that will include Python and Java. So I don't know if that answers your question or not, though. Oh, different error. Okay. Okay, which questions I get a lot?
Because you mentioned it's sensor data, so all the sensor will come with error bars, right? I mean, all your measurements will have some kind of error, and you have correlated noise or systematic errors or all kinds of trouble.
Yeah, oh my gosh. Sensor data is both the most challenging and fun data in the world. So before I joined H2O, I was dealing with a lot of sensor data. So in this one, I actually did not tackle that problem, right? It was a very kind of straightforward nonlinear transform from this 23-dimensional sensor space plus a couple other dimensions on which running into the remaining useful life space. Yeah, I've dealt with, sensors come with bias, they come with noise in them. We don't have that kind of like inherently built into the machine learning piece of H2O yet. We also are working on some pieces to not just have uncertainty. The input uncertainty we don't have, but we're working on things around prediction interval uncertainty. So expect to see some things in the next few months, maybe some wrappers around that, kind of like our H2O ensemble package that could help. But I'd love to hear more things, so like that you think could be there, because that feedback would be really useful as we tackle these sorts of challenges.
Hi, I have a question. So how you partition or design the window size of your data to fit the time series data into your GBR algorithm?
Yeah, so it's really, the input variables are the sensor measurements that were remaining. So I think there were 23 to start with, and there were 6 after you take out the ones that don't vary. It turns out that it's not unusual to get sensors that are either faulty or just read constant all the time. So once you take out all the ones that don't vary, you end up with 17 or so. I forget the exact number. I'd have to count them. But yeah, then I took each one at just each point in time, because all you're getting is a sample of the sensor data from each cycle of these jet engines, and then push that through to do the transformation into the predicting the remaining useful life. So it's really kind of a straightforward. There's no phase space embedding, or even there is a set of summary statistics that are provided that are the summary of how many times each engine was in each one of its cycles. Because it turns out every time you cycle a jet engine, you would expect it to be one step closer to its remaining useful life, except for these faults that have been introduced that make it degrade faster, and you're trying to find the faster pieces.
So it means that you use the timestamp as the feature name to the feature. Yeah,
just an individual cycle of the engine is what provided the row. The observation was a single snapshot of it. It's not gigantic sensor data like it's not at 10 hertz. It's at one cycle measurements, just randomly picked, which was really fun, because you didn't even get it inside of a single operating mode. You just got one snapshot at one point in time. It was a challenging data set. You can download it off of the NASA website and have fun with it.
Okay, then the output will be the next set of the data you predict.
Yeah, so I'll publish it. You can take a look at the code, and then it'll answer your question.
Thank you. Yeah. Thank you.
Awesome.
Any others? All right, so let's thank our speaker.
Thank you.